Alright, so we said that we can only use this empirical rule if the data are approximately bell-shaped. In some cases, the data are not bell-shaped, and they are usually skewed right, skewed left, or we just don't know. For data that are skewed, or the shape is unknown, we use what's called Chebyshev's inequality. So this is a little bit confusing. For any data set or distribution, it says at least, and it gives this funky formula, blah percent of the observations lie within k standard deviations of the mean, where k is any number greater than 1. So k represents the number of standard deviations, and k has to be greater than 1 for this to work. So this is the formula. You don't have to memorize it. However, it is not on your formula sheet, so I'll make sure it's provided for you on the test. I'll make sure it's given to you. So the formula is 1 minus 1 over k, standard deviation squared, times 100%. It's relatively simple. It's just a calculation. And so using Chebyshev's inequality, if we want to know what percent of the data are within 2 standard deviations, then k equals 2. So remember the formula is 1 minus 1 over k squared times 100. So this time k is 2, so 1 minus 1 over 2 squared times 100. You can just put that directly into the calculator using parentheses, 1 minus 1 over 2 squared times 100. If you type that in correctly, it should just spit out 75. If you'd rather work it by hand, that's 1 minus 1 over 2 squared is 4. And that's times 100. Another way to write that is 1 minus 0.25, so 1/4 is 0.25, times 100, which we know is 0.75 times 100, which is where we're getting the number 75. You can work it by hand, you can throw it in the calculator, either way is fine with me. So whatever number they give you for k, you just put it in, type it in, and it spits out the answer. So in this example, 75% of the data would be within 2 standard deviations of the mean. So it's the same process if we want to know the percent of data within 3 or 1.5, whatever number they give you, as long as the value is greater than 1. This formula will work. So there might be a question on the homework that mentions that the data are, the shape is unknown or that the shape is skewed, and instead of using the empirical rule, you would use Chebyshev's inequality. All right, that finishes up section 3.2. Remember, we're not covering section 3.3 at all, not even mentioned in the curriculum. So we're going to move on to section 3.4. So section 3.4 is about measures of position and outliers. Position and outliers. We're going to discuss something called a z-score. This will be something very important later on in the course. Percentiles, quartiles, something called the interquartile range, and we'll learn how to calculate outliers. All of this is important, but the big idea that would carry on forward after this chapter is z-scores. So a z-score helps us determine how far the individual data point is from the mean. This is what they call standardizing. So this standardizes the data so that we can compare data sets from different scales. So if you're recently out of high school, you took the SAT or maybe you took the ACT, and the SAT is based out of one scale of numbers, and the ACT is based on a totally different scale of numbers. And students often ask, well, which one did I do better on? Because the numbers are totally measured differently. How am I supposed to know? So a z-score will help us compare things that are on different units. Same thing with miles per hour versus kilometers per hour. If you're interested in your speed, I drove in a different country where kilometers per hour was the speedometer, and it was really confusing because I was used to miles per hour, and it's a different scale. So we can compare these if we use what's called a z-score. So in the book, it kind of explains that. And it gives you a formula for a population z-score and a sample z-score. These are actually the exact same calculation. They use mu for population, they use x bar for sample, but it's all the same. They use sigma for population, they use s for sample. So I don't want you to think of this as two different calculations. It is the same formula, whether you have a population or a sample. And there's a bottom note that says the z-score is unitless, no units involved. It has a mean of 0 and a standard deviation of 1. I'll try to explain that as we go. Before we move on, I want you to look back on your formula card. You can cross out these 1, 2, 3, 4, 5 bullets on the right hand side. You can cross all those out. Below those, these two bullets are the z-score formulas. There's for population, there's for sample. Again, they're pretty much the same thing. So you can cross all that craziness out, and I want you to kind of highlight where your z-score formulas there are. While we're looking at this, let's go over to the first column. You have population mean and sample mean. Remember, you can use your calculator for those. It tells you how to calculate the range. The next two bullets are on standard deviation, which we're just going to let the calculator do for us. So remember that can be done in the calculator. Then here's a reminder of how to get variance, which is not that big of a deal for this class. So really the empirical rule and the z-score, and then these last three bullets we'll discuss in the next section. So those kind of help you focus in for your formula chart. So here's your z-score formulas. You do not have to memorize them, and we will use them rather frequently. All right, let's see how this is done. So here's an example from the book. It says determine whether the New York Yankees or the Cincinnati Reds had a relatively better run-producing season. So we're comparing here. The Yankees scored 859 runs and play in the American League, which has a mean number of runs of 721.2 with a standard deviation of 93.5. So that's the Yankees information. And change colors here. The Reds scored 790 runs, but they play in the National League, where the mean number of runs is 700.7 and the standard deviation is 58.4. So if you just look at the numbers, 859 and 790, well, obviously the Yankees did better. But if you're a little bit more careful and you compare the Yankees to their league, to their American League, and we're going to compare the Reds to their league and see, relatively speaking, relative to their league, who did better. So this is where a z-score comes in. So we're going to do the z-score for the Yankees. And it is their score, 859, minus their average, 721.2, divided by their standard deviation, 93.5. When you put this in the calculator, if you want to type it all in at the same time, put parentheses around the top, because the calculator follows order of operations. So parentheses, 859 minus 721.2, close the parentheses, and then divide by 93.5. So parentheses are important. If you don't want to use parentheses, sometimes I'll just type in the subtraction, hit enter, and then do the division. So you can either do it as two separate operations or use parentheses. If you do not use parentheses, let me just show you what happens. The calculator is going to divide first and then subtract, and you get a totally different answer. So make sure to type this in correctly. We're going to round to 2 decimal places. Remember, 4 is the standard for precision. For z-scores, we typically round to 2 decimal places. So we should get 1.47 for the Yankees. And then for the Reds, z-score Their number was 790 minus their mean, 700.7, over their league standard deviation, 58.4. Type that in correctly. Don't just trust me, make sure to type it in yourself to make sure that you're getting the right numbers. This is 1.53. So let me try to explain this with a bell curve. This means that on their curve for the Yankees, their mean for the league is 721 with their standard deviation. A z-score of 1.47 means that they scored 1.47 standard deviations above their mean, above their league's average. For the Reds, their league's average was 700.7. Remember, we count 3 and 3. They scored 1.53 standard deviations above their mean. 1.53 standard deviations above their mean. So if we're trying to say who did better relative to their league, it would be the Reds, because they were higher on their curve. They did better. They did above average a little bit more than the Yankees. And so the answer to the question would be the Reds were relatively better compared to their league. So the higher z-score means it's further away from the mean and higher up on the curve. Hopefully that makes sense. Here's another example. So it says in example 1, the team with the higher z-score was said to have a relatively better season. With negative z-scores, we have to be careful when deciding the better outcome. So let's say Bob and Mary are running a marathon. Now let's think about if we're running or racing. If you're racing, you want a faster time. A faster time is a smaller number. So Bob finished the marathon at 213 minutes, where the mean finishing time for men is 242 with the standard deviation of 57. So the z-score for Bob would be 213 minus 242 over 57. And if you type that in correctly, it should give you a negative number, which should make sense because his time is less than the average, and that gives you a negative 0.51 for a z-score. So he was faster than average. Mary finished the marathon in 241 minutes, where the mean finishing time for women was 273 with a standard deviation of 52. So Mary's z-score should also be negative because she was faster than average, and she got a negative 0.62 if you round z-score. So Mary did better. Mary did better because she was faster, and when we're racing, we want a faster or lower score. So she's more standard deviations below the mean, which is what you would want when you're racing. So you really have to read the situation and decide, do I want a more negative z-score or a more positive z-score? Usually, you want to be further away from the mean, whether that's above or below. You want to be further away. If you're racing, you'd want to be more negative. If you're trying to do test scores or anything like that, you want to be more positive. So example of z-scores. Now we have percentiles, and students overthink this, so just keep it simple. Do not overthink percentiles. The median of the data is said to be at the 50th percentile. 50% of the data are below the mean and 50 are above. So a percentile is a measure of the percent of data that are specifically below that percentage. And below is the key word here, below that percentage. So if you are at the 90th percentile, you are taller than 90% of your population. 90% of your population is below your height. That means you're relatively If you are the 10th percentile, you are only taller than 10% of your population. That means that only 10% of people are below your height. So you are relatively short. So percentiles always start from the bottom. So 0 up to that percentile, so it's always below. Anything below that percentage is where you're measuring from. So on a curve, 0% would be at the bottom, 100% would be at the top, 50% is right in the middle. We'll go over that in just a second. So the percentiles and the empirical rule kind of go hand in hand, and I'll kind of show you how that works. I'm going to find the same sheet we broke down with these numbers, and I'm using that same example of test scores. So if you find the slide with the empirical rule, we're going to use that same information. So here's the page with the empirical rule. So we went over on the previous video. So using the empirical rule, determine what score is at the 16th percentile. So if you remember, after one standard deviation below, everything below one standard deviation, if you add 0.15, 2.35, and 13.5, it adds up to 16%. So 60 would be at the 16th percentile. That means that 16% of scores are below 60. And it says what scores at the 50th percentile. Remember, the dead middle, right in the middle, is 50th percentile, so that would be 70. And this one's sometimes a little tricky. What scores at the 97.5th percentile. So starting from the bottom, if we add all these numbers up, except for the top 2.5%. So these two represent 2.5%. So everything below that is 97.5%. So it starts from the bottom and goes up. Sometimes it's easier to look from the top and subtract. So 90, the score of 90 would be at the 97.5th percentile. So empirical rule and percentiles go hand in hand. All right. So from percentiles, we get what are called quartiles. The data can be divided into 4 quartiles, like quarters. And this, again, goes hand in hand with the percentiles. So the lowest 25% of your data, which is from the 0 to the 25th percentile, we call Q1, or quartile 1. The 25th percentile is the value we use to cut off quartile 1. The lower 25 to 50th percent, so 25th to 50th percentile, we call Q2, or the second quartile. Instead of calling it 2Q though, we call it the median, because the 50th percentile is where the median falls. So instead of calling it Q2, we call it the median. The upper 50 to 75%, which is from the 50th percentile to the 75th percentile, we call Q3. So the value at the 75th percentile is Q3. Then the highest 25%, or the top 25%, from the 75th percentile to the 100th percentile, we call Q4, but instead of calling it Q4, we call it the maximum data value. So the 100th percentile is the very highest value in your set. So we have Q1, instead of Q2 we say median, Q3, and instead of Q4 we say maximum. Q1, the median, Q3, and the maximum are the different quartiles. We've already learned how to do one var stats. And let me show you using those test scores we were looking at earlier. Whoops. So stat edit, here's those 10 test scores. If we go stat calc 1 var stats, you get the X bar, you have the sums, which we don't need, the standard deviations, the N is the sample size, Then if you scroll down, the first number is the minimum, Q1, median, Q3, and maximum. So here's your values, Q1, median, Q3, and max. So that's all under one var stats, and you just scroll down. So scroll down to see all of that information. All available in the calculator. So from the quartiles, we get something called the interquartile range, the IQR, interquartile range. It is specifically the third quartile minus the first quartile. And it is on your formula sheet. There it is, IQR, Q3 minus Q1. So it will be provided to you on the exam, IQR. So this kind of tells us where the middle 50% of the data are, neglecting those potential outliers. So this summary tells us if the distribution is symmetric, we use the mean and the standard deviation to report. If it's skewed, we use the median and the IQR to report. We're not really reporting things, so it's not too important for this class, but if you are going on to graduate classes, it will be important to know which measures to use to report your information. This takes us to how to calculate an outlier. So extreme observations we call outliers. And depending on the data set, there might or might not be outliers. And there's a specific formula to measure those outliers. A lot of students just like to guess. So some points might seem like outliers and they're not. Others may not seem like outliers and they are. So we're not going to guess, we're going to use the formula. So here I took out of the book. It says determine the first and the third quartiles of the data, Q1 and Q3, which we get from the calculator. Compute the IQR. So we can get all that from the calculator. And then we determine something called a fence. A fence serves as a cutoff point for determining outliers. Anything outside the fence is an outlier, anything inside the fence is not. So we have a calculation for what's called a lower fence, Q1 minus 1.5 times the IQR, and an upper fence, Q3 plus 1.5 times the IQR. Now 1.5 was decided upon using some calculus, which we're not going to get into. And these two formulas you do not have to memorize. Once again, they are right there in your formula chart. So very little memorization in this class. It's more about understanding what these numbers represent. So there's your fence calculations. So if a data value is less than the lower fence or greater than the upper fence, we call it an outlier. So let's see how this works. Here's a set of data. So this table is different amounts of money. So we have all these different amounts of money. And if we're just glancing at this, some students might say, well, 21,000 sure does look like an outlier. Or maybe 180 looks way too low. Here's another one, 189. So we might look at the data and kind of guess what we think might be outliers, but that's not how we're going to do it in this class. We're going to put all of these values into L1 and get our one var stats. So let's do that. Stat edit, clear out L1, put in your values. Any order, I always go across so I don't get lost. And you just put all your values in. Always double check as you're typing that you didn't skip a number or type in an extra number. Just always take your time here and do it right the first time so you're not frustrated later. Just putting in all the values I see. Kind of keep up with where you are. Again, make sure to do this yourself with your calculator so that you kind of know how it works. Just watching me will not ensure that you know how to put all these values in. So there's 18 values. Your cursor should be on space 19 when you're done. Stat calc, one var stats. We need to get Q1 and Q3, so I'm going to go down. Q1 is 735. Q3 go down is 4668. So we need those two pieces of information to get what's called the IQR, which would be 4668 minus 735, which if you subtract is 3,933. So just Q3 minus Q1, whatever that number is. Now we're going to use the formulas. Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR. So Q1, 735 minus 1.5 times 3933. Your calculator will be able to use the order of operations and calculate this all at the same time. 735 minus 1.5 times 3933 gives you a big negative number. Sometimes this will work out to be negative 5164.5. This says that any value in our table less than this is an outlier. Now this is a big negative number. I don't have any negative numbers up here, so there are no lower outliers. No lower outliers. Let's use the upper Q3, 4668 plus 1.5 times that same IQR. And we can just type that in. That gives us, you can still see that, 10567.5. That is our upper limit. Now, looking in our table, the outliers, whoops, 21,147 is actually an outlier. Anything else bigger than 10,567 is an outlier, so that's the only outliers. So 21,147. I think these were the monthly salaries of employees at a company. So that must be the president or CEO or owner making $21,000 a month. Must be nice. So that's an upper outlier for this set of data. Anything bigger than the upper fence. So that's how to calculate outliers. Pretty simple. Just some number crunching. And that will come in handy in just a minute. So that finishes section 3.4, and it ties into section 3.5 on what's called the 5-number summary and a technique called box plots. It's a graph called a box plot. So I like section 3.5. This is a quick and easy way to numerically and visually summarize the data and find outliers. This is very nice, easy way to get some information from your data. So it's called the 5-number summary and box plots. So the official 5-number summary include the lowest data value, which we call the minimum, or min for short, the first quartile limit, which is Q1, the second quartile limit, which remember we call the median, the third quartile limit, Q3, and the highest data value, which is the maximum, which we abbreviate and say max. So it's the minimum, Q1, the median,